Hi everyone. So in this video, we're going to be looking at Module 5. So Module 4, which we just finished, or if you did watch the video, we're looking at the older brain structures, right? The brain stem, the amygdala, the hippocampus, all these portions of the brain that are basically at our unconscious level, right? They're what keep our bodies going. To some extent, they also regulate our emotions and things like that with because they're connected to the hormones and all that. But they're primarily done at an unconscious or unperceived way. Today we're going to be looking at the newer parts of the brain, the parts of the brain that are far beyond that of any other living thing as far as we can tell, within humans at least. Okay, so as always, quick reminder, make sure you do the quiz after this with the random bits of information that I will be giving you throughout. And yeah, and D2L is where you find the PowerPoints and all that kind of stuff. All right, all the go-to normal stuff. So let us begin. So cerebral cortex module 5. The cerebral cortex is going to be the outer layers of the brain, essentially, and then the different lobes and things like that of that make it up. Okay, so first, cerebral cortex. This is the second slide. The functions of the cortex, part 1. It's the ultimate control and information processing center of the body. So this is the part of this is where our decisions are made. Okay, any conscious thinking, to some extent, even reactions and things like that are going to be processed within the cerebral cortex. Right? We talked a little bit about like the inner brain. You might have reflexes and things in there, right? It doesn't take thought to necessarily have a reflex. The spinal cord is all you technically need, but anytime that you're like, I should, given this situation, I should do this. There's a little fluffy kitten sitting there. Maybe I should pet it because it looks so soft and all that kind of stuff. Okay. And then the fact that I can perceive it as soft when I touch it and things like that, those are all going to be processed within the cerebral cortex. Anytime I have a perception where I can, my interpretation of the information coming in, generally that interpretation is done through the cerebral cortex. There are 20 to 23 billion brain nerve cells within every person's brain, and 300, give or take, trillion synaptic connections. That's a very large number. There are more synaptic connections within an individual's brain than there are stars in our galaxy. Okay, so that is a lot of connections. Okay, cerebral hemispheres, so paired and covered with intricate fabric of interconnected neural cells. So the sphere is essentially, the brain is divided into two portions. We have a left side of the brain and a right side of the brain, okay? And there's actually a little like fin of relatively hard material that goes between the two sides. And there is a very, very thick nerve that runs between the two sides that keep the two sides of the brain connected and talking with each other, basically. All of this, beyond just that nerve, is also covered with essentially like a very fine, very thin layer of fabric, okay, that is essentially just nerve cells that allows the speed of the brain communicating from side to side to go even faster. Interestingly enough, the layer of nerve cells essentially wasn't discovered until after we developed these new tools that allowed us to see the brain without actually like taking the brain out of the skull. It's extremely fragile, like unbelievably fragile. And in autopsies, when they would remove the skull, basically to look at the brain, generally that very thin layer would be removed with the skull unintentionally. And so it wasn't even, they didn't even think it was there, or they didn't even know it was there until they were able to start measuring the electrical pulses of the brain and things like that without the person being dead. So the cortex of each hemisphere is divided into 4 lobes, which are separated by different fissures. If you ever seen a human brain, it looks kind of like a raisin, right? Lots of wrinkles and lots of little like canyons basically that run through it. Those are going to be some of the different fissures that basically break up the different portions of the brain. Okay. These two cerebral hemispheres also make up approximately 85% of the overall brain mass. The weight of the brain, okay, 85% of the weight is in this cerebral hemispheres. So these newer parts of the brain take up a very large portion of our overall energy that our brain uses. And it's going to do all the specialized stuff, right? Our communication, our ability to decipher words coming at us, our ability to communicate back, like I am doing right now to you, and then the intentional motions, our perceptions, like I said, of eating, all those kinds of things. What are we tasting? What are we smelling? How do I interpret this information coming through? All of this is done in this portion of the brain. So yeah, that's basically what we're going to be looking at. Another thing to be aware of, the brain, you might have heard people say that we only use 10% of the brain. I've heard that over and over and over again. I don't know where that started, but it is 100% false. The entire brain is utilized, which makes sense, right? The brain uses over 20% of our overall energy of our body. So our entire body, the brain, this little thing up here, relatively small, right, uses 20% of the overall energy expended by our body. It would be silly for the brain to be wasting that much energy if it was only using 10% of it. We use the whole thing. Now, whether or not we do that well or do that efficiently, that probably is an individual by individual basis. So that might, if you ever watch anyway, yeah, you look at most of modern pop culture stuff and it seems kind of yeah, that makes, that I can see where people might think we're only using a small percentage. But yeah, we use the whole thing. So be aware of that. Slide 3, and first random fact. When mice live in the wild, they only live about 6 months on average, primarily because they get eaten by other things. Mice are like the bottom of the food chain as far as animal things go. In captivity, they can live up to 2 years, give or take. That's a pretty old mouse, though, if it makes it past 2. But yeah, so mice live 6 months in the wild approximately. Anyway, random fact. Here we go. Back to the things. Terms to learn. You're going to learn about the different lobes. Okay. There's an image here on this slide, and if you're following in the book instead of on the PowerPoint, you can find the same image on page 59. But it shows basically the separation of the 4 different lobes within the different hemispheres. Okay, and they're gonna mirror each other to some extent. So the left side and the right side are going to look approximately the same, kind of like the left side and right side of our face look approximately the same. You have the frontal lobes. This is the portion of the cerebral cortex lying just behind the forehead, involved in speaking and muscle movements and in making plans and judgments. Essentially, the frontal lobes, this is actually the last portion of the brain to fully mature. So the brain, early on, right, right after conception, within a few weeks, the early stages of what will be the brain's full glory have already begun to form. But the brain doesn't fully develop until around 25 years old. And even then, it's still moving forward, but it reaches its full potential, basically, by around 25 years old. And the frontal lobe, this prefrontal cortex, this portion right here in the very front, right behind your forehead, is actually the last part of the brain to fully develop, to fully mature. So, but this is also the part of the brain where actually, to some extent, this is what gives you the ability to look at a thing and go, oh, that's a great idea, or that might not be so good, which is why, part of the reason why, if you're, let's say you're an adolescent, okay, you're like 14, 15, 16, 17 years old, something might seem like a great idea in the moment, but upon afterwards, and you're like, that was really stupid. Part of the reason why we have a tendency of doing those kind of stupid things in adolescence is because the frontal lobe isn't fully developed yet. Okay. It's also why a lot of people, when you experience, for those of you who have 25 or older, around the age of 25, a lot of people have kind of a moment where suddenly those things that they liked doing before that were kind of crazy aren't as appealing anymore, right? There's a reason why extreme sports athletes are generally under the age of 25. There's a handful of them that keep doing it older, but the majority of them are going to it just kind of fades out after 25. There's also a reason why Marines are generally 18 years old, right? They have enough energy and thinking to get you in there, but after 25, you're like, the idea of getting shot at constantly doesn't necessarily seem that appealing anymore. Okay, and you also, when this develops, we lose that sense of we feel invulnerable, or we feel basically like we're invincible. Okay, sure, that killed so and so, but I'm different, kind of a thing. We do this even if we're like no, that's not what I think. It in fact is. It's a proven fact. That's just what humans do, right? We assume that we can survive things, even if other people haven't done it. It's okay. I'm invincible. We also have an assumption when we're like in adolescence and like that we are not going to live that long. I know for myself, personal experience, and this is all getting connected to the brain developing. I assumed that I'd be dead by age 30 because I was doing all kinds of extreme stuff. Here I am close to 40, and my body is now letting me know about all those stupid choices I made in the past, but I survived, right? So thus the long-term thinking doesn't usually kick in until after the age of 25. Okay, enough of that. Frontal lobe. The parietal lobes is the portion of the cerebral cortex lying at the top of the head and toward the rear. It receives sensory input for touch and body position. So again, top kind of towards the back. This is going to be what allows you to basically play sports and things like that, where you move your body through space effectively. This is also going to be what keeps you from falling over every time you try to stand up. These are your processing of what is in your environment and how to maneuver through it. Okay. And also is what allows us to like pick up things like pins and stuff like that, right? Without this portion of the brain, it wouldn't happen, basically. Occipital lobe is the portion of the cerebral cortex lying at the back of the head, includes areas that receive information from the visual fields. We're going to talk about that more when we look at senses, but remember, the light waves come into the eye. That information is turned into basically electrical impulses. Those electrical impulses go from the front, where the eyes are, through the brain to the back, where it is then processed, broken down, and then re-put together to give us sight. Okay, we'll look at that more when we look at the senses and we look at sight specifically. But yeah, eyes are going to be working. There's also a point where they crisscross in there. Left eye goes to the right side of the brain. Right eye goes to the left side of the brain. Although there is also some messaging that makes it into both. Okay. And then temporal lobes. Portion of the cerebral cortex lying roughly above the ears includes the auditory areas, each of which receives information primarily from the opposite ear. So left ear talks to the right side of the brain, right ear talks to the left side of the brain. And in this communication, the crisscrossing there, again, it's also what allows us to be able to tell where a sound is coming from. The distance and the difference in the speed of which the sound hits us, our brain interprets very rapidly that the right ear hears a little bit faster than the left, or vice versa. And so you'll know, like, you hear a bang and you look. The fact that it happened on that side, we know where to look. If you've lost hearing in one ear, you won't have a clue where the sound came from. You'll know there was a sound, but it could be anywhere in your 365-degree field. Okay. 360-degree field. Sorry. Ears, days of the year. Anyway. Okay. Slide 4. Functions of the cortex, part 3. So motor functions. Motor cortex is the rear frontal lobes, right? Just right behind, boop, right here. Controls voluntary movements. The fact that I just went, boop, made myself going on like Mickey, that's because of that. Okay. Mapping the motor cortex, the body areas requiring precise control occupy the most cortical space. Forster and Pinfield basically were the ones that discovered this. So things like your fingers, where you need very fine, detailed information. You are going to experience much more. There's a lot more of that portion of the brain that is dedicated to that. The other area is going to be the mouth. Those are going to be two areas where you can primarily have information. We're going to have a slide here in just a second that looks at this, kind of the perceptions of it. But this is also why the detailed information, so I have a highlighter and a pen. If you take two pencils, okay, and you touch them to the back of your hand versus the palm, you notice that the palm has a lot more sensitivity. So you'll actually feel, you can have them closer together and still feel that there's 2 points of pressure. Even more so if you go to the fingertips. Okay, back of the hand, you have to separate them a little bit more, right? Back of the neck, you have to separate them pretty significantly, right? Like, because essentially the back of the neck isn't an area that we use primarily for exploring the world. So therefore, there's not very much of the back of the neck dedicated to the feeling within the brain. Okay. You need to know if you got like scratched or something or cut, but knowing if you're getting touched or trying to like touch something with the back of your neck, that's not how we explore the world. Okay. Brain-machine interfaces. So device implants are understudied to detect and facilitate motor cortex activities in humans. Implants recipients have learned to direct robot arms with their thoughts. Later in the semester, actually, we're going to be looking at, there's a video of, they've been doing this with monkeys primarily, but they've hooked up monkeys. They have a little thing that basically runs up the back of their head to a computer, and they can hook it up to a robot arm, and the monkey can actually move a robot arm intentionally to the point where they can stick a monkey in a box with its head sticking out, and the monkey can feed itself with this robot arm while its real arms are inside the box and you can't control it. Amazing stuff. The idea here is that they can then potentially going to be able to take that and put that to like prosthetic arms or things like that, where you can then essentially have full control, assuming that the prosthetic is capable of it, of full range of motion and the dexterity and everything, just as your normal arm. You also potentially could run robots and things in the distance through your brain with these connections. Weird stuff. Okay. This is another area of psychology. If you really want to get into it, you can explore that. If you want to kind of combine engineering and psychology, that might be an area to look at. So, slide 5, function of the cortex parts. This is that weird imagery here, but showing kind of approximately where the majority of our brain area is taken up. So again, the tongue, the fingertips, and the mouth are going to be the primary areas where we have the most space is taken up by those areas. This is also why babies, when they're exploring things, put things in their mouth immediately. And the mouth has a lot of different nerve cells in it that allow for very specific exploration, right? You take a pea and you put it in your mouth, and that pea feels huge inside your mouth, and that's because basically there's so much information going to the brain, and the brain is using so much of that. Okay. Okay. Random fact number 2. Lettuce is a member of the sunflower family. Well, there you go. Lettuces. And you have a salad, you're eating sunflowers. Anyway, slide 6. Functions of the cortex, part 5. Sensory functions. Somatosensory cortex. So it receives incoming messages from skin senses and movement of body parts. In front of partial lobes, parallel to and behind motor cortex, and the body region sensitivity equals larger somatosensory cortex. Okay, so essentially the somatosensory is, again, it's kind of what allows us to move through our environment effectively. It's also what allows me to swing my arms all over the place, and I'm not knocking stuff off my desk all the time, right? Unless I'm kind of clumsy, but anyway. So yeah, visual cortex receives input from eyes, sends information to the other task specialized areas, so face identification, emotion detection, face recognition. So essentially, again, that information goes to the back of the brain. Okay, the brain breaks that apart, rebuilds it, so it pulls apart the motion, the color, the outline. All of these factors are pulled, and like all these pulled apart, and then re-put together, and then sent out to the other parts of the brain to basically figure out what it is you're looking at. Okay, which is then sent back, and then you have a conscious thought or experience of it. We have different parts of the brain that are specifically set aside to face recognition, for example. So I see a face. The fact that I can tell the difference between like my wife and another woman, or my children and just random children, at schools or things like that, are due to that part of the brain. If that part of the brain is damaged, you cannot. I couldn't tell the difference. I could probably tell the difference between a woman and a male, okay, to some extent, but I couldn't tell the difference between two specifics. Okay, and it depends on the intensity of the loss. If all I've seen is the face, and I've lost everything else, essentially, you can't perceive the individuality, right? The brain basically just doesn't remember. You're like, you can tell you're looking at a face, but you can't tell whose face you're looking at. Okay. Okay. There's an image too on this slide. You can find the same picture on page 61 in our book. It's an fMRI looking at the brain. This is actually kind of an interesting one. So when you close your eyes, for an average person, the part of the brain, basically the visual cortex of the brain, kind of slows down, right? Still produces some things to some extent, but not at a very high level. So image A is an average person with their eyes closed. Image B is a person with their eyes closed, and don't ask me how they got permission to do this one, but they did. But the person is on LSD, and the red and dark colors basically within the brain are showing brain activity. And so essentially, a person even with their eyes closed, if they're on LSD, so the color again is it's blood flow basically, which is showing how active the brain is in this area. This person will experience hallucinations. In other words, their brain is like, I don't know what to do with all this energy. There should be something here. And so therefore it creates new imagery, even if you're not actually seeing anything. Basically the brain is like, if this energy is being used, it must be because of something. And if there is nothing, I'm just going to make it anyway. So there you go. That's to some extent how hallucinogens work. We'll look at that more in depth when we look at the drugs later on again this semester, but interesting stuff. Slide 7, functions of the cortex, part 6. Sensory functions, auditory cortex, right? Receives information from ears, circuitous route from one ear to the auditory receiving area above the other ear. We talked about that. So the left ear is talking to the right side of the brain, and the right ear is talking to the left side of the brain. And it's found right here on the sides of the temporal lobes. Okay. So yeah, there you go. That one's easy, pretty straightforward. Keep on moving. Slide 8. And your third random fact. The Hobbit, J.R.R. Tolkien's The Hobbit, has been published in 2 editions. The first edition actually had Gollum betting and losing the ring willingly. So if you ever actually get a chance, if you're a Tolkien fan, you can actually get your hands on the original copies sometimes. Not like, I mean, if you get your hands on a first edition, like that's amazing. But you can get there are out there pieces where you can see the original storyline, where basically it follows Bilbo's story that he tells the dwarves. So there you go. He changed it up. He changed up that when Lord of the Rings began to be written. He tweaked it basically to make it fit with the Lord of the Rings better. So there you go. Random fact. The Hobbit. Okay, slide 8. Functions of the cortex, part 8. Association areas. So cerebral cortex area is not involved in primary motor or sensory functions is going to be what this area is. It's involved in higher mental functions, so learning, remembering, thinking, and speaking. And it's found in all 4 lobes. Okay. The prefrontal cortex is going to be that enables judgment, planning, social interactions, and new memory processing, can alter personality and inhibitions when damaged, and it disconnects moral behavior from behavior. This is also the part of the brain that generally is affected when you get like drunk. Okay, so if you drink alcohol, the prefrontal cortex shuts down to some extent, which is why you make stupid choices. And it's also why it's the filter, essentially, of your brain, right? It's the thing that goes, you probably shouldn't say that. That might be offensive. People might not like that. And you just say it when you're drunk, okay? Because the prefrontal cortex is basically turned off. This is also why little kids have a tendency of just blurting out things, because the prefrontal cortex is still developing. That filter has not been installed, okay? Parietal lobes enable math and spatial reasoning. Parietal lobes is the part of the brain where Albert Einstein's brain actually had exceptionally large parietal lobes. His ability to basically do spatial reasoning was far above the average person's. Then the right temporal lobe underside enables face recognition. So the right side, underside of the temporal lobe is where you basically is stored everyone's faces, and the fact that you can see, a face and know it as a face. Let's see, I got some related notes here. Yep, that's basically it. Oh, real quick, I think I mentioned the God spot before, where some psychologists are trying to find a specific point in the brain that basically lights up when we are having a religious experience. They've actually found that there's more than 40 distinct areas of the brain that light up when we're experiencing a religious thing, like such as meditation or prayer and things like that. There's no one spot. So anyway, interesting random fact. That's not actually a random fact. That's just another random fact that's not officially one. Don't look for that one on the quiz. Okay. So the whole point of that, and the whole reason I pointed that 40 different points is actually to remember or to realize there's no specific spot that only has one job. It's the whole brain working in conjunction with each other, with every other part of the brain, that allows us to essentially experience the world consciously. Okay. Slide 9. Response to damage. Attributions for many brain damage effects. So severe severed brain and spinal cord neurons do not regenerate. Real quick, it used to be believed actually that by adolescence, and then they moved it to 18-ish, and then they moved it to 25. And then today they actually changed it again. They used to think that the brain, once it reached that point, basically you had as many neurons as you were ever going to have, and they were just slowly dying. They have found that there are neurons that can regenerate, and or if they are damaged, they can repair themselves. What they've discovered also, though, is that there are some that once they are damaged, they're just gone. Okay, that still is true. Spinal cord neurons, and like so up here, especially like in the brainstem and stuff, oftentimes it's going to have a hard time regenerating if it's able to at all. So specific areas are pre-assigned for some brain functions. There are some parts of the brain that if they are damaged, you just lose that ability. Okay. If it is damaged when you are younger, there is a chance that the brain will realign and basically repurpose a different part of itself to take over that role. But the older you are, the less likely that is, which is why things like stroke, if you have a stroke as a kid, which is extremely rare, but you're much more likely to bounce back from it. The older you are when the stroke occurs, the less likely you are to recover from it fully or well. So, okay. Neuroplasticity and reorganization, this is basically parts of that, may occur after serious damage, especially in young children. So again, smack to the head, or you have a stroke or something like that. You are capable of, the brain is basically capable of rewiring itself or rerouting things and repurposing different parts of itself. Makes unused brain areas available for other uses. So for example, in the case of blindness or deafness or damage to one hemisphere. If somebody's born blind, okay, so the eyes, you're either born with no eyes or your eyes are in a way that they just aren't capable of receiving information. The brain will repurpose that whole portion, the visual cortex portion of the brain, for other things, which is part of the reason why people who are born blind, their other senses will be stronger, because basically the other senses then can utilize that part of the brain. So in fact, they do have stronger senses. It's not just that they're more aware of them. The senses, the ability of those senses to perceive things are higher because a larger portion of the brain is reserved or is used for those things. Okay. On that note, real quick too, this week we have I have a video in here called Jill Bolt Taylor, My Stroke of Insight. I'd like you to watch that. I'm not going to have a quiz on it or anything like that, but I'd like you to watch it. It's an interview with a woman who is a neuroscientist who had a stroke, basically a brain aneurysm, or shut down part of her brain, almost killed her. She survived. Okay, but she talks about, because she was conscious during this process, and because she was a neuroscientist, she took exceptional note of everything that she went through. So really interesting talk, about 20 minutes give or take. Totally worth the time. Okay, but neuroplasticity, again, the brain is amazingly capable of reshaping itself, and that continues throughout the entire life, right? You could be 90 years old, and assuming you're alive still and not dead, your brain is reshaping itself, rewiring itself, given the new experiences that you're having. Okay. Neurogenesis is new neurons may be produced, migrate elsewhere, and form connections. And so this is something that they didn't think used to be the case after a certain age. Now they found that it continues to happen throughout life. So yeah, our brain is capable of moving. There are certain activities that increase the chances of this. Exercise is is one that they found increases neurogenesis significantly. Reading, specifically reading paper, so not on a screen, but there's something about looking at a book or a magazine, something that's written on paper, and reading it that causes the brain to produce new neurons to some extent. So yeah, exercise, reading. There's also certain herbs and things you can take that can help with this. But okay. Slide 10, the divided brain. And real quick, a random fact, the last random fact, a cluster of bananas is called a hand, and a single banana is actually officially a finger. So there you go, bananas are hands. Okay, the divided brain. Splitting the brain. Corpus callosum severed. So the corpus callosum is a relatively rigid fin, essentially, that separates the two sides of the brain. There were several different kinds of seizures, okay, and they were actually life-threatening seizures. And they found that when the corpus callosum was severed, the seizures stopped. Okay, but when the corpus callosum was severed, it also basically cut the communication between the left and the right hemispheres of the brain. For the most part, everything else has remained intact. Okay, so their personalities remained pretty much the same. Their IQ levels or intellect remained about the same, give or take. Their overall motor function remained about the same. The biggest thing is that the life-threatening seizures ceased. But then they started looking at some other things. So visual information sharing ended. Left side of the brain no longer was capable of crossing over and talking to the right side of the brain, right? The optic chasm basically was severed. And so with that, it now holds the one side of the brain specific. The eyes don't share information back and forth. The brain doesn't communicate both sides. Behavior and agency were affected. So because of that, kind of how you were working with things would shift because of this. Left hemisphere gives rational goal-related orders. Right hemisphere gives conflicting demands. And so basically the brain is actually arguing with itself at the same time. And this is happening within you unconsciously to some level. But because they're not able to communicate each other back and forth. The right side of the brain is kind of the free spirit. The left side of the brain is like the get the business. But the one side of the brain is going to be experienced more consciously, and so because of that, it can cause issues. Okay. And there were a few circumstances where, in fact, the different sides of the body almost seemed to rebel against each other, where the right hand and the left hand would actually, like, it wasn't like, like some of the movies were like, but it was like the right hand would write something and you weren't consciously aware of the fact that you were writing it and things like that. Okay. So weird stuff. Slide 11. You can find an image that I'm looking at here in, where are you? Page 66. Okay, I'm sorry. And there's an image on the other one you can find actually on page 65. But on page 66, that's basically all we have here. What they did, this was an experiment they did with people who had where the brain was split, essentially. The corpus callosum was severed. They had a screen with a dot in the center, and they said, look at the dot. Okay. They would flash two words, H-E, and so he and art, one on one side, one on the other side of the dot. And it's projected fast, so you don't have time to like scan it with both eyes. It just is boom, and it's there. Long enough for you to perceive it, not long enough for you to like study it. They say, what word did you see? And they ask the person to say the answer, and the person would say art, the right side of the brain. Okay, that's where that information was processed. They'd ask to point with your left hand. Okay, and the person would basically point at the opposite. Okay, left hand, left eye saw the left side. Okay, again, where the processing occurs. So yeah, weird stuff. Okay. You have two minds going, and you would be potentially not aware of this happening. Let's see, slide 12. Right-left differences in the intact brain. So the right hemisphere, increased activity with perceptual tasks, modulates speech, allows for making inferences, organizes self-awareness. And that's actually a big thing. So the right side of the brain is what allows you, like if I were to tell you a dad joke, the reason it's a joke is because the right side of the brain reads that you shouldn't have taken that literally, right? The left hemisphere is where language control occurs. It's what allows us to basically speak, and it's also what allows us to receive that information and decode it, but we don't get all the nuances. Okay. So sarcasm and all those kinds of things where you're saying, like, oh, this is just the greatest day ever. Okay, if I say it like that, the right side of the brain is like, that doesn't sound like the greatest day ever. Left side of the brain is like, the greatest day ever. This must be the greatest day ever. Okay, takes it very literally. Left side of the brain is also going to be primarily math tasks. Now, I don't want you, like, pop psychology has sold us a bill of goods on this one. So, you take a quiz, take this quiz and find out if you're left brain or right brain dominant. Oh, you're right brain dominant. You are creative and you're going to be terrible at math. That's not true. Okay. The brain is very much working in conjunction with each other, right? Both sides are working connectively. It's not as simple as like, if you take this test and if you're creative, then you must be right brain, therefore you must be left-handed. Okay, all that kind of stuff is false. Left-handed people aren't necessarily right brain dominant. Okay, and right-handed people aren't necessarily left brain dominant. Otherwise, 90-something% of the population would be left brain dominant, and that's not the case. In fact, most people aren't left or right brain dominant. They just happen to have learned to follow certain things, right? Like some people learn that, oh, this is a more successful survival strategy, basically, compared to somebody who's maybe more creative. Okay, so creativity versus logical thinking, all that kind of stuff. So humans have unified brains with specialized parts. The brain is working as a whole. Every part of it is working in conjunction with other parts of it, but there are specific areas of the brain where it has specific jobs. Okay. Think of a big corporation, right? You have a whole bunch of people working. They might have specific jobs that they're doing, but all of their individual jobs come together to do the overall thing. Okay. Engineers designing stuff. You got machinists building this stuff. You got people who are packing it and all that kind of stuff. The brain is basically all like to some extent like that, but at the same time, it's all working in unison together. Okay. And with that is pretty much the module. I do want to take a real quick note. I forgot that there was no slide on this, but in the chapter, on page 63, there's a picture of Phineas Gage. Phineas Gage was both lucky and unlucky, depending on how you want to look at it. He was working on a railroad, probably not singing, but he was putting a charge into the ground, and he was tamping it down like they were supposed to, but something went wrong, and the charge went off, and it shot a very heavy rod through his left cheekbone and out the top of his skull. Okay, there's brain between the left cheekbone and the top of your head. It knocked him over. He stood up, walked over to the foreman and went, a rod just went through my face. Conscious, completely conscious. Okay, it didn't knock him out. And that you can see the image on this on page 63. That shows where the rod went through his face. Took him to the doctor. Doctor didn't believe they were like, there's no way that this went through your head. He coughed, and he proceeded to cough up what the doctor prescribed, or said it was a teacup of brain, basically fell out of his head. And he was like, okay, so you did. Survived, seemed totally fine, recovered fine, other than he's missing his left eye now, but seemed totally fine. Until his friends started seeing that his personality had changed. And this is one of the first glimpses that the frontal part of the brain actually is connected to our personality. He became more surly and things in the days following this. We don't know exactly what happened to him. He just kind of, we know when he died about 12 years after this event. We don't have a clue about like personality and stuff that he stabilized or things like that, because he just kind of drifted away. But interesting stuff. Okay. It's worth a look. There's tons of information online if you want to find videos and stuff of him. There's a bunch out there about that. But anyway, thought I'd point that out. So again, make sure you do the quiz. 4 random facts. We'll be looking at genetic and evolutionary psychology and behavior in the next module. So hopefully that's something that interests you. There are a couple of videos on here: The Chemical Mind, Crash Course Psychology number 3, and Meet Your Master, Getting to Know Your Brain, Crash Course Psychology number 4. That I'll give you a really quick summary of all the information we just covered in this module and the module before. So that might be something worth looking at if you want to kind of get a refresher on all this material. Anyway, have a wonderful day, everyone. Good luck with the quiz, and I will see you in the next video. Have a great one. We'll see you.